Hi everyone, I'm Tal from MC Square, University of Michigan. In this tutorial, I'm going to show you how to take EELS spectrum on Thermo Fisher Scientific Spectra 300. So we'll start with the standard stem alignment, and just to make sure we have a good beam for the EELS acquisition. So let's navigate to the sample and fix the eccentric height. And we'll zoom in and focus on one square. Okay, let's go back to the TM user interface and let's center the mono. And we'll set the beam current to 150 picoamps. And we center the beam over the hard disk detector. Reset the beam shift. Reset the stigmator. Let's go back to check the image. See, we got some contamination. Let's move to another region. So focus on one square. Okay, looking good. And let's just run the auto score. Looks like it's finished. So next, let's set up the beam for EELS acquisition. So we can click the EF to show the EELS entrance aperture. And you see our bright field disk is now way bigger than the EELS entrance aperture. The best size of the bright field disk will be about half size of the EELS entrance aperture. And we know we can make it smaller with the camera lens. So here, let's just change it to the smallest camera lens, which will give us the smallest possible bright field disk. But if we compare the bright field disk with the EELS entrance aperture now, we see it's although smaller, but it's still not the half size of the entrance aperture. We still want to make it smaller. So to further reduce its size, we'll have to go into a special mode called EF stem. So let's go to the EF10 tab and turn on the EF10 mode. And you see now the mode indicator shows now it's in EF stem. And now you see the bright field disk is much smaller. And then we'll have to make it bigger. Then of course we can do that with the camera lens. So let's just make it bigger. Let's do 410. And now you see the size is about half size of the EELS entrance aperture. Let's center it to the EELS entrance aperture with this diffraction alignment. And let's check the image. So in this mode, you see the image on hard disk is very bad. That's because the bright field disk is too small. To get a better image, you can use this DFI detector, and you see the DFI image looks very similar to the hard disk image that we got under the normal condition. We can zoom in to check the image real quick and make sure our beam is still good. Okay, let's focus. So looks like there's still some astigmatism, and we can fix it quickly using the OptiStem. Okay, so except for some contaminations, the image now looks good. So now we can push the EELS button on the external scan controller and switch the signal to Gatan. Okay, so in GMS, we go to Home, STEM SI, and we see this scan palette. And if we click View, we should be able to see the image. But here, very important, we'll have to remove the DFI detector because it shadows the signal from the ADF detector in the GIF. And now you see what we can get in GMS is very similar to the hard disk image that we got under the normal condition. And next, let's just find a region of interest. And because this sample is just a cross grading, everywhere is the same, we'll just randomly pick up one block, center it, and let's try taking the EELS spectrum in here. So let's stop the scan, and if we click the spot button, and we got this beam park. For EELS alignment, we'll have to move this beam to somewhere we don't have sample. Ideally, we want to do it in an empty hole, but if we don't find an empty hole, like in this sample, it's okay to just do it on the carbon film. So on the Spectral, we have two cameras for EELS. We have the normal GIF camera and we have K3. So in this tutorial, we're gonna use K3. If for some reason you wanna use the GIF, it's the same as what you do on the Talos. So let's use the K3. So you will have to change it to single just for alignment and change the energy to 0. So you see automatically the lifetime has been changed to 0.1. And just to protect the camera from being overexposed, let's start with a very small number of the lifetime. So we'll decrease it to 0.03, which is the smallest allowed number. And for exposure, we can just start with a small number like 0.01. Now let's go here and right click on K3 and say insert. It's gonna take some time for it to be inserted fully, so let's just wait patiently. So now it's inserted. And here you can see the dispersion now is at 0.9 EV per channel. So you can click this dot 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 and change the dispersion. So according to what elements you want to map, you can change the dispersion so that all the elements will fit in this energy range. You can check the edges of different elements by clicking on this periodic table. So here you can click on any element, and here it will display all its edges. We'll just use 0.9 for this demo. So next we can come to the EELS palette and click view, and we can see the zero loss peak is showing nicely. So a very common problem you may have here is that when you start view, you don't find the zero loss. In this case, there could be a few possibilities. The most common situation is that you have something that's in the beam path which blocks the beam. For example, this bright field detector. So I have just inserted the bright field detector, and let's go back to GMS, and we see our zero loss peak disappeared. So if in this case, let's just go ahead and retract the BF detector. So now it's no longer blocking the zero loss, and we get the zero loss peak back again. Another possibility is that over time, because the zero loss can drift, there is a possibility that it drifts outside this energy range. So see, now I am shifting it. So you see now it is out of the energy range that we can see, and of course you won't be able to find the zero loss peak. So what you can do, you come to this adjust and use the arrow key to shift it back, and now here is the zero loss. And you can come to this tune gif and click align ZLP, and it will automatically shift the zero loss peak to this 0 point. Next, we can click on this autofocus. So now it will do autofocus. So most of the time, this is sufficient to get a small enough zero loss peak, and the full width half maximum of your zero loss peak will define your optimum energy resolution. So see, it started from about 2 eV and now it's getting 1.7 eV. At this dispersion, 1.7 is kind of what you can expect. If you use smaller dispersion, I think you can get to about 0.8 eV. Okay, so it's finished, and the final energy resolution is 1.75. That should be good for elemental mapping. So if you want to do manual alignment, you can click on this 2D. So now you can see the real 2D image on the K3, and click user tune here. It will zoom in really onto this zero loss region. So here you just want to adjust it so that it shows up as a straight line, and the width is as narrow as possible. So to increase the count a little bit, we can increase the lifetime to 0.1. Just do not increase it too much, otherwise it will damage the camera. So here you can use the DE to fine-tune the zero loss position. The FX will focus it along the dispersion direction. The FY will rotate it. We will align it to the vertical direction to minimize the width of the zero loss peak. And this SX will just make it a moon shape. So if you see a moon shape, it can be corrected with the SX adjustment. The SY will correct this 8 shape. So if you see the beam is distorted like an 8, you can correct it with SY. So let's touch up the SY and make it as sharp as we can. Touch up FX. Alright, so this is about the best we can get. Okay, next, let's focus the sample. Looks good. So here in this scan palette, you see there are 2 buttons, search and preview. So search is like a quick search, and preview is usually set to a slow scan. And the parameters can be set if you click this gear button. So here you see the search is set to 1 microsecond of dwell time, and the preview is 20. So let's take an EELS map just on this center square. But before that, I'd like to give it a slow scan. The reason is that you see between the fast and the slow scan, there is a very small image shift. The EELS acquisition is going to use the slow scan setting, so it's important to get a slow scan image so that the scan position is accurate. Next, let's set up the scan parameters in this EELS palette. There are 2 ways to take EELS spectrum. One is the single, and here in the periodic table we can define what elements we're going to take. So this will define the energy range, and of course in this single acquisition we will not be able to take the position of the zero loss. So we'll only take the core loss of the elements we are interested in. So if I set to the carbon edge, now you see the energy range has shifted. The zero loss is no longer in this range. The EELS spectrum we're seeing now starts from about 200 eV. That's because the carbon edge we selected is at 286 eV. But just keep in mind that the zero loss position will shift even within the acquisition. So it is always nice if we can take the zero loss peak as our reference, just like the XPS data. Later we can correct this energy shift if we have a nice reference. So we can achieve that using this dual EELS mode. In this mode, we can acquire 2 energy ranges at the same time, and this energy ranges can be set individually in this EELS palette. So you see now the low loss is showing the zero loss peak, and the high loss is set to the carbon range that we have just set. Of course, you can set it to any range according to the elements you are going to map. Let's set up the scan parameters for each range. Now you see the zero loss peak in the low loss is showing red color. Red means the detector is already saturated. To avoid this detector saturation, we'll have to reduce the lifetime a little bit until it goes back to this bluish color. And also we can make this exposure time smaller so that our scan becomes quicker. So we're getting about 30-ish counts for the zero loss peak. This is usually enough for this energy calibration. And next, let's set up our core loss. Because the core loss signals are not as strong as the zero loss peak, we can increase our lifetime. So let's gradually increase it and make sure the detector isn't saturated. So looks like this 50% will work. So this yellow color means it's about to saturate but not yet saturated. So we can drag around the beam and see the spectrum, and we should confirm the edges of the elements we are going to map is showing in this live spectrum. And we already see the carbon. So next, let's check the gold, which is around 2200 EV. So looks like the spectrum is noisy. We can increase the exposure time a little bit. The gold M edge is going to appear around this region. So we can hold the shift key and drag the mouse on this live spectrum so we get a live background correction. It feels like there is some signal, so maybe we can give it a try with this setting. So let's stop the live scan and let's go to the SI acquisition. We can select 2D array to define the scan area. Let's adjust this rectangle ROI to be on about 1 square. So center it on 1 block. This pixel time here defines the dwell time for the EELS acquisition. Because we are using the dual EELS, we can set the pixel time to be the sum of the low loss and the core loss exposure time. Because you see this low loss exposure time is very small, so we can just set to 0.01 the core loss exposure time. We can also define the number of pixels we're going to scan, and the total time needed will be displayed over there. We can set the scan time to be a few minutes. There are some other parameters we can set. This live button, when it's turned on, it will show the live EELS spectrum at each pixel during the acquisition. And this drift button allows us to set up the drift correction. It allows us to set up the drift correction frequency to be like every few seconds, or a few pixels, or a few rows, or a few frames. So because our sample is very stable and we are at a not very high MAC, so for this acquisition we will not do drift correction, so we'll turn it off. This BFDF button allows us to also take a stem image on one of the stem detectors. So once it's turned on, it will also take a scan image. This sub-scan button only applies to the scan image that we're going to take. So it increases the sampling rate when it takes the scan image. So basically when it takes this ADF image, it rasters beam within 1 pixel, so that our result stem image will have more pixels than our EELS maps. This pass option allows us to do multiple scans for this EELS acquisition, and of course it's gonna increase the time. We'll revisit this option later, but just for this acquisition, we'll set it to only 1 scan. So before we start the scan, let's do a final slow scan of the image just to confirm that our sample isn't drifted during our setup. And then if we click this capture button, now the acquisition has started. Let's just wait until it finishes. So during the scanning, we can hold on the control key, drag our mouse so that we can check the EELS spectrum at different positions. And we can take a look. The palladium should appear over here, just right behind the carbon edge. Now the scan has completed. We can go to this elemental quantification palette, select the elements we want to map. So carbon, and we have palladium, and we have gold. And we'll have to go to this edge setup to see the curve fitting results for different edges. So see here, the software is able to fit some gold edge here, but if I drag it to the carbon region, and there's no fitting. So this is looking good. And let's check the carbon. So carbon is very obvious, and we can drag this fitting range and mostly confirm the background fitting. So just visually check if the fitted background is along this curve. There are different models for background fitting. We usually use power law, which gives usually the best results. But there are some situations that the power law cannot give a good result, then we can choose others. So because the palladium is so close to the carbon edge, this overlap with CK is automatically selected. And if we drag it on the nanoparticles, we see GMS can indeed fit some palladium signals here. Another important option is this include plural scattering option. Because we have the zero loss, the low loss region also recorded, we are able to turn this on so that GMS will do the deconvolution to minimize the multiple scattering events. So the edge fittings are all good. Then we can click on this map button. So see, there are a few different options, and again, because we have the low loss recorded, we are also able to do areal density map and atomic volume density map. So let's select all of them and let's see what we can get. Okay, so these are just the signal integrals, and we can see the carbon, palladium, and gold maps. The carbon is on the carbon film, the palladium and the gold signals are on all the nanoparticles, which makes sense. And these maps are the atomic fractions, and we also have the areal density and the volume density maps. So that's just a simple demonstration of how to get an EELS elemental map. So let's go back to this low loss spectrum and take a look at the zero loss peak. And you see when I drag the ROI around, you can see there is indeed a small shift of the zero loss positions. That means the energy range has been shifting during the acquisition. So because again we have this zero loss peak as our reference, we can correct this energy shift. So to do that, we drag our mouse on it and make an ROI, and we can go to SI and select align SI by peak. Okay, yes. Alright, so now we get a stem SI processed. So now if we drag this ROI, let's zoom in to the zero loss region. So see, when we drag our ROI, now the zero loss stayed all the time at the zero position. With this calibrated EELS dataset, we can try to generate the elemental map again. But honestly, I don't think we will get anything different, because the elemental maps are not very sensitive to the exact edge position. Another benefit of having this low loss peak acquired is that we can generate a thickness map. To do that, we can click on this EELS low loss button, and we come to this EELS analysis and click on the thickness. So now we got a thickness map, and on this map each data point is scaled to this inelastic mean free path. So this inelastic mean free path is a constant, but depending on different materials and different acceleration voltage, its value is usually around 100 nanometers. We can also generate a absolute map. If we want to do that, we can come to the EELS menu and see there is a log ratio absolute. So we can just set up the parameters. The convergence angle we are using is 30 millirad. The collection angle is defined by this EELS entrance aperture. And we know we have set the beam to be about half size of this EELS entrance aperture. So we can just make a very rough estimation that our collection angle is 60 millirad. So we can put the 60 here, And next, we need to input a effective atomic number. So for the pure element, there's a function that we can choose from the periodic table so that it inputs an estimate for us. So now if we click OK, now we get an absolute map. Each pixel on this map is in the nanometer scale. Of course, this is based on the estimated mean free path of gold. So at the last, we want to save the data. So to save the data, you have to save this piece called STEM SI. This includes everything, the image and the spectrum. And you can save the elemental maps by right-clicking the tab and select Save Workspace As. So that's all for this tutorial. If you have any questions, feel free to leave a comment under this video. You can also send me an email. Thank you for watching.